Welcome to unit number 3, higher order differential equation. Today we are going to see for linear differential equation with constant coefficient. So first, the general form of linear differential equation is a0 dny by dxn plus a1 d to the power n minus 1 y of dx to the power n minus 1 plus and so on a n y is equal to f of x. It is equal to, if we take y is common in all the terms, so a0 d to the power n by dxn plus a1 d to the power n minus 1 by dx to the power n minus 1 plus and so on an multiplied by y is equal to f of x, where a0 a1 up to an are constants. So if we denote d by dx as d. Now in previous two videos in vector differential calculus we have studied operator del. Now in differential calculus operator is d. That's why this all the methods which we are going to study to find out solution of differential equation is by operator method, and here operator is d. So d is a differential operator and it is denoted by d by dx. It may be d by dt, depending on the problem we change this d. So here d is a differential operator and it is denoted by d by dx. So d to the power n become d to the power n by dx to the power n. If it is d to the power n minus 1, then it become d to the power n minus 1. So this equation become a0 d to the power n plus a1 d to the power n minus 1 plus and so on an multiplied by y is equal to f of x. Now we denote this whole term because whole term is in terms of d. D to the power n, d to the power n minus 1, d to the power n minus 2 and so on. So this term is denoted by phi of d multiplied by y is equal to f of x. Now general solution of this equation number 1 is given by y is equal to cf plus pi, or sometimes we denote it by yc plus yp, where cf is nothing but the complementary function and pi is particular integral. Now first thing we need to study about this differential equation, there are two variable, one is dependent and another is independent. Now here y is dependent on x, that's why y is called as dependent variable and x is called as independent variable. So to remember this, whenever the differential equation is in terms of y and x, then y will be dependent variable and x will be independent variable. It may be it is dependent on this numerator as well as denominator. Whatever the numerator variable, it is dependent variable, and denominator variable is independent variable. So dependent variable is always a solution in terms of independent variable. So whatever the solution we get here y, that will be cf plus pi and it is in terms of x only. So here two things are important, complementary function and particular integral. So first, what is homogeneous differential equation? In this equation number 1, phi of t multiplied by y is equal to f of x. If this right hand side is absent, then f of x becomes 0. If f of x is equal to 0, then it becomes phi of d multiplied by y is equal to 0. And this term is called as homogeneous differential equation. And this homogeneous differential equation has solution y is equal to cf only, or y is equal to yc only. Why? Because right hand side is absent and on right hand side we get particular integral. So this is homogeneous differential equation. Non-homogeneous differential equation means this f of x term is not equal to 0. Means it remain as it is, phi of d multiplied by y is equal to f of x, and we get solution, both the solution, complementary solution as well as particular solution. So y is equal to cf plus Pi is the solution for non-homogeneous differential equation. For homogeneous differential equation, solution will be y is equal to Cf only. So this is non-homogeneous differential equation. Phi of d multiplied by y is equal to f of x, and solution will be y is equal to yp plus yc. Now method to find out complementary function or complementary solution. So first phi of d multiplied by y, our general equation is phi of d multiplied by y is equal to f of x. Now to find out Cf only, we do not consider this right hand side. So we put this phi of d multiplied by y is equal to 0. We equate this left hand side is equal to 0. Then we get auxiliary equation. Auxiliary equation is phi of d is equal to 0. Phi of d means whatever the term which is in d here multiplied by y, so only that d term we equate it to 0. Or sometimes we put d by m, so it becomes phi of m is equal to 0. So after substituting phi of m is equal to 0, we get roots of this equation. So roots are denoted by m1, m2, m3 and so on. This may be d or you can denote it by m. So there are total 4 cases to find out complementary function. First case is, case 1 is roots are real and distinct. If the roots are real and distinct means which roots? We got roots of this d, that is m1, m2, m3. If it is a quadratic equation, then we get 2 roots. If it is a cubic equation, then we get 4 roots. If it is a cubic equation, then we get 3 roots. If it is a fourth order equation, then we get 4 roots. Like that, depending on the order of differential equation, we get roots. So whatever the order of differential equation, that much roots we will get here. Now case 1 is roots are real and distinct. If we have roots m1, m2, m3 and so on, then it is real and distinct, then we can write Cf as c1 e to the power m1x plus c2 e to the power m2x plus c3 e to the power m3x and so on. For example, if we get roots of d are suppose 2 and 1, then how to write Cf? Cf can be written as Cf is equal to c1 e to the power this m1 is 2, so 2x plus c2 e to the power x. So in this way, if the roots are real and distinct, both are real and distinct, then we can write c1 e to the power 2x plus c2 e to the power x. Now this order is not important. You can write either c1 e to the power x plus c2 e to the power 2x. Then this will be okay, because you can write first 1 and then 2. It's okay, no problem. Next, second case is roots are real and equal. So if m1 and m2 are real and equal roots, and remaining roots, that is m3, m4, m5 and so on, are distinct, then we denote this 2 equal roots by m. So m1 is equal to m2 is equal to m. Then Cf becomes c1 plus c2x e to the power mx plus c3 e to the power m3x plus c4 e to the power m4x and so on. So if 3 roots are equal, suppose m1 is equal to m2 is equal to m3 is equal to m. If 3 roots are equal, then Cf can be written as c1 plus c2x plus c3x square multiplied by e to the power mx. Means we increase one constant as well as we increase power of this x. Here x to the power 0, here x to the power 1, then x to the power 2. If one more root is equal, then c4 x to the power 3 e to the power mx plus c1, c2, c3 we have already written. Next will be c4 e to the power m4x and so on. So we can write like this when roots are different. We can write like this if the roots are equal. So if 4 roots are equal, we will get c1 plus c2x plus c3x square plus c4x cube e to the power mx. Next, case 3. If the roots are imaginary or complex. If the roots are complex and distinct, means if the roots are imaginary, then if m1 is equal to m2 is equal to alpha plus minus I beta and m3, m4 and so on are distinct, then CF can be written as e to the power alpha x c1 cos beta x plus c2 sin beta x. Now this first term is real part and this is imaginary part. So whatever the alpha is here, e to the power alpha x c1 cos beta x plus c2 sin beta x, plus, and if roots are another roots are different, then we can write by using first case c3 e to the power m3x plus c4 e to the power m4x and so on. So suppose we have m roots is m is equal to 1 plus minus I. Now compare this root with alpha plus minus I beta. What is the value of alpha? Alpha is equal to 1 and beta is equal to coefficient of this I. So alpha is equal to 1 and beta is equal to 1. How to write CF for imaginary roots? It is equal to e to the power alpha x in bracket c1 cos beta x plus c2 sin beta x. Now in this question we don't have another roots, only we have root is 1 plus minus I. So we write up to this only. Now it is equal to e to the power alpha value is 1. So e to the power x c1 cos of beta is also 1. So cos x plus c2 sin x. c2 sin x. So this is CF if the roots are imaginary. One more example, if the roots are m is equal to plus minus 2i. Plus minus 2i. Now again compare this with alpha plus minus I beta. What is alpha value? Here alpha is, no term is present means alpha value is 0. And what is the value of beta? Alpha is equal to 0 and beta is equal to 2. So again how to write CF? CF in general it is e to the power alpha x c1 cos beta x plus c2 sin beta x, which is equal to e to the power 0x in bracket c1 cos of 2x plus c2 sin of 2x. Now e to the power 0x means 1. So this is c1 cos 2x plus c2 sin 2x. So in this way we can write CF for the roots are imaginary and distinct. If the roots are imaginary and distinct, we can write CF like this. Next, if the roots are, next fourth case is if the roots are imaginary or complex and equal. If the roots are equal, that is m1 m2 is given as alpha plus minus I beta, means m1 is alpha plus I beta and m2 is alpha minus I beta. m3 m4 is given as alpha plus minus I beta, then m1 and m3 is same. m1 is alpha plus I beta and m3 is also alpha plus I beta. So m1 m3 are same, m2 m4 are alpha minus I beta and m5 m6 are distinct, then CF can be written as e to the power alpha x c1 plus c2x into cos beta x plus c3 plus c4x into sin beta x. Again here also we have same thing. Whenever the roots are equal, we write c1 plus c2x multiplied by here, because it is imaginary, we multiply this c1 plus c2x to cos beta x, c3 plus c4x into sin beta x. If three pair of imaginary roots are there and it is equal, then how to write this CF? We can write CF for three pair, it is e to the power alpha x c1 plus c2x plus c3x square cos of beta x plus c3 is over here, so c4 plus c5x plus c6x square multiplied by sin of beta x. So this is the CF if three pair of imaginary roots are equal. Now for example, if we have Roots are m is equal to plus minus 2i and plus minus 2i. Now both the roots are same, plus 2i minus 2i minus 2i. So how to write here? First equate it with alpha plus minus I beta. Now what is the value of alpha and beta in both the root? Alpha is equal to 0 because here no term is present, and beta is equal to 2. So CF can be written as e to the power alpha x in bracket C1. Only two pairs are same. So C1 plus C2x multiplied by cos of beta x plus C3 plus C4x multiplied by sine of beta x. So this is e to the power alpha x. Alpha is 0. So e to the power 0 is 1. C1 plus C2x multiplied by cos 2x plus C3 plus C4x multiplied by sine 2x. So this is the CF if the roots are imaginary and same. So in next lecture we will discuss some examples on these cases. Thank you.